And my job is to chair this session. I want to get started as close on time as I can. So I'm going to be brief in my introductions. And I think that's easy in this case because my first speaker is a well-known person that I'm sure you all know, Bruce Rittmann. Bruce has a long and storied career which early on began with the honor of being the first winner of the Clark Prize. But Bruce is one of the people I have long admired for insight in biological processes. So we'll look for what he has to tell us here. He's going to talk to us about photosynthetic microorganisms to generate renewable energy feedstock. Bruce.
Oh, okay. Let's see if this works. Yeah. It worked. Okay, good morning. I'm happy to be here. Thanks to the Clark Prize and NWRI people for inviting me. And I am going to talk about the official title, which is Using Photosynthetic Microorganisms to Generate Renewable Energy Feedstock. That was the title I gave when I was asked to give the talk. But I thought about it a little bit, and I think there's another title that's even better for today, and I'm just going to tell you what my alternative title is. And it is Water as part of the solution to renewable biofuel, not a roadblock. And actually, I prefer this title for today and in general. So let's get on with it. And I'm going to begin with some context. And the context is sustainability. That is sustainability of human society. And our biggest challenge across the board for human society looking to the future is unsustainable use of fossil fuels. And we know this is the case. Depletion of petroleum reserves is a big issue. Geopolitical, economic distress is all over. But, of course, the one that is really even more pressing as we look to the future is the global climate change. And, it's a very simple concept. The Earth is taking in more energy than it's putting back to space, and we're warming up. And the key driver for that is CO2 from burning of fossil fuels. And, we're going to have a lot of bad outcomes from this, but I like to think that the terrible storm we had that wiping out major sections of New Jersey and New York is just the harbinger of what we can expect to have happening more, and we're going to get pretty tired of it as a society. So we'd like to do something about it. CO2 is the main driver, and so I took some CO2 concentrations from various years up here, just to illustrate the change in CO2. And pre-industrial revolution, about 280 parts per million. After the industrial revolution started, first with coal and then with other fossil fuels, it started to go up. The key thing here is you can see it's going up faster and faster. The time intervals between my years, the time intervals of the years is getting shorter, but the rate keeps going up. So this is going up very fast. Now, the IPCC hopes, this is kind of aspirational, that we might stabilize around the middle of the century at around 450 to 550 parts per million, but that's really pretty aspirational. For me, however, I really have a different goal, and I think we've had enough. We've had enough increasing in global greenhouse gases, and why don't we set as a goal to just stop? Why don't we just stop today? We've gone up high enough. We're around 390 parts per million today. Isn't this enough? Let's stop. What would it take to stop today? Well, there's a year up there, I put it up there, where we would have to go back to the fossil fuel use to hold steady where we are now. It is approximately 1950. So if we went back to the worldwide fossil fuel use of 1950, about a third of today, we could basically hold steady where we are at CO2. So I figured this is a good goal. It's aspirational as well, but let's make that a goal, and as my goal, at least a driving aspiration behind the research that we're doing and I'm going to talk to you about today. So what I want to do is find replacements for what we use fossil fuels for today, particularly for high value uses in things like transportation. And so first thing we have to do is figure out how big is our challenge. So here's a slide on scale, and at the top you can see that human activities these days worldwide consume energy at about 16 terawatts Of that, about 84% comes from fossil fuels. That adds up to around 13 terawatts of energy use rate in the world today. And it's going up, as you know, and that makes it harder. But even at today's rate of 13 terawatts, this is a very large number. It's a lot of energy that we use. Okay, so there's a little more on scale. There's our 13 terawatts. On the good side, the sun sends us energy at a rate of 173,000 terawatts. So upside potential is there's plenty of renewable energy out there from the sun. It's just, of course, it's not in a form that we can use to do things like fly our airplanes. On the downside, if you look at the natural ecosystems and agriculture and how much energy it captures from the sun via photosynthesis, it's around 140 terawatts. Now, this is a very dangerous number here. You can see that human society is using energy to run itself at about 10% of what all of the natural and agricultural systems take in from the sun and turn into what we call primary production. And so this is really pretty dangerous on the situation, but it's also why we love using fossil fuels so much, because there's plenty of it out there and it's high density. Okay, so what I'm going to propose here is that bioenergy can play a big role here in the large-scale production of renewable energy to replace fossil fuels if we let water work for us, not against us. So the theme of my talk today is making water be part of the solution, not the roadblock. And to do that, I'm going to contrast what we shouldn't be doing, and that is a lot of crop-based biofuels. They've gotten a bad reputation, particularly corn to ethanol, but some of the other ones aren't so good either. And not the only reason, but a large reason is that they are huge water consumers and water polluters. Jerry Schnur, who's in the audience today, chaired a wonderful NRC report that looked at this and pointed this out very clearly on it. So, again, consumes a lot of water, particularly for irrigation, and of course it's a big polluter. Now, we don't want to do that. That isn't going to make water part of the solution. That makes water the problem. So how are we going to change this around so the water works for us and not against us here? And so I'm going to introduce this, I'm going to start with two principles of bioenergy and then show how we can apply these in a constructive way. First principle. Ultimately, the sun is the only source of renewable energy. It's the only major source of renewable energy. And we have a lot of it, 173,000 terawatts coming in all the time. But it's diffuse, not in a form that we can use to run our human society. So we need to get it transformed to forms that we can use. Second principle is that the energy, that useful energy, is in the electrons. So we have to get electrons in places, materials that our human society can use. And I've listed some down here: electricity, methane, hydrogen, hydrocarbon fuels. These are obviously good things. Our society knows how to package electrons so they're useful for us to drive our cars and fly our airplanes and light our lights and do all that. Now, if you combine those two principles together here, you get this diagram that's shown here, the diagram on the left, and the words on the right, or the same information, just in words. So the key thing about bioenergy is you start with the sun. That's the source of the energy, of course. And the source of the electrons that we're going to make high energy is water. There's plenty of water around. That's not a problem. And what we do is we use photosynthetic organisms to capture the sunlight energy, take the electrons out of water, and put the electrons into CO2, reducing it into biomass. Organic things, often the parts of the photosynthetic microorganisms. Some of those things we can use directly. Think of burning the log in the campfire, or more likely we'll convert these through various biological or other means to things like hydrogen, methane, and hydrocarbon fuels that we can use to drive our cars and things like that. When we take those carbon-based materials and we oxidize them, we get our CO2 back. So this is good. It's what we call a carbon-neutral loop. The CO2 goes into the fuels and gets put back, but we're not increasing the net amount of CO2 into the atmosphere this way. We're just looping it around, so it's carbon neutral. This is what we aspire to. Now, in comparison to fossil fuels, I start off by saying that it's basically the same principle. Photosynthesis occurs, CO2 is reduced, electrons come from water, you make the biomass in various forms. The difference, of course, is that photosynthesis occurred hundreds of millions of years ago. And so we're simply mining photosynthesis over hundreds of millions of years and burning it up in 100 or 200 years. And so you can see, on the one hand, the wonderfulness of this. We get all this concentrated photosynthesis, hundreds of millions of years concentrated. That's the good part. It's so convenient. The bad part, of course, is we're throwing up a huge amount of CO2 into the atmosphere that's been sequestered for hundreds of millions of years. So that's our conundrum. So we'd like to get around this. Now, as a context point here, for what my main story is, I'm going to talk about residual biomass. This is the stuff that comes from agriculture, the food system, human activities, human wastewater, and other things. And the DOE has done some calculations, and if you could collect all the residuals, the things that we don't actually use, but are what we might call the waste materials or the residuals, and you could collect all of them and convert them into useful energy, you could meet roughly 25% of the world's energy supply today. Now, that's not going to solve our problem. Remember, we need to replace at least 2/3, but it would be important, and we should do that. And those are things like Perry McCarty talked about just in the previous talk on this. But the key is 25%, if we could collect it, we can't, isn't nearly what we need to do, maybe more like 2/3 of it. So we have a long ways to go. So yes, residual biomass is not enough, and that means one thing we need to do is we need to produce a lot more biomass. And as I show here in green letters, we need to do a lot more photosynthesis to capture the energy from the sun, and we need to do it in an environmentally acceptable manner. That's the key thing. More photosynthesis, but in an environmentally acceptable manner. So how is that going to work? Well, first of all, we use photosynthetic organisms, and we have a choice. We have plants. You know what plants look like. You see them every day. And we have microorganisms, of which I've shown one photomicrograph of these. So we have a choice. We can use photosynthetic plants or photosynthetic microorganisms. Which shall we choose? Well, I have made a little listing here, a comparative listing of 7 bullets comparing plants to photosynthetic microorganisms. And the bullets line up. I won't cover all 7 today, I don't have time, but I'm just going to point out a few of them. The first thing has to do with use of land. Plants, of course, grow on arable land. They must. Microorganisms don't grow on arable land because, well, they don't grow on land anyway. They grow in water. So we eliminate the competition with the food supply when we use microorganisms because they don't grow on the soil anyway. 2, aerial production. Oh, given we use some land, how much do we use? And the aerial production rates converting sunlight energy into the biomass energy is somewhere between 10 and 100 times greater for microorganisms than it is for plants. Actually, plants are quite inefficient in terms of converting sunlight energy into themselves. And microorganisms are much more efficient, between 10 and 100 times greater. So you can imagine if we need to make terawatts worth of energy, we're a lot better off going with the one that has 10 to 100 times greater yield. Third is the issue of water consumption and water pollution here. And of course, agriculture is a huge, huge source of water pollution, particularly nutrients. And it consumes water. It's right up there with electrical power generation in terms of the biggest water consumers in America. And so agriculture and plants is a huge, huge consumer and polluter. A well-designed microbial system can be very water efficient. We can eliminate uncontrolled evaporation, and there's no transpiration. We can have closed systems that allow us to keep the nutrients in so that we don't let them just fly out into the environment. So we can then have a winning situation here. So, obviously, the answer is, if we really want to use bioenergy, we should go with photosynthetic microorganisms. Okay, now I'm going to tell you just briefly about what we're doing with photosynthetic microorganisms at Arizona State University. And our focus in our group is on producing new biomass or biopetrol from photosynthetic bacteria. And we're not using algae, we're using photosynthetic bacteria, or more specifically cyanobacteria. And we use a particular genus, Photosynthesis. That's our favorite one to use. This is a very robust, fast-growing organism, harmless in itself. And I show a picture here, a photomicrograph of one of these. And this is a good photomicrograph because it shows one of the nice features of it. If you look here, you see all these little lines running through it here. Those are internal membranes, or so-called thylakoid membranes. That's where the organisms, when they're really happy out there in the sun, got nutrients available, where they put the apparatus to do photosynthesis. And, of course, membranes are largely lipids, and lipids are oil. Yeah, you see the pattern here. So we are actually creating organisms with quite a large amount of feedstock that would be oil feedstock that could be used eventually to replace petroleum. And these are fairly high lipid content naturally, and we can do some modifications to them to make them higher in lipid content as well. And we leverage this with advanced photobioreactor systems here that we work on in our center, and to make these high efficiency systems. Here's some pictures of things in our system. Here, there's the sun. There's Photosynthesis. And over here on the left is a picture of one of our laboratory scale systems where we do more fundamental, highly controlled research with these organisms. And out here on the right is our rooftop system, 2,000 liters exposed to the sun, the real sun. So how does this work? The value proposition is we're going to create a large amount of what I call new biomass. And you see I made it green because this is photosynthetic new biomass here. And we can use this then to supplement the normal capture of energy and carbon by natural and agricultural photosynthesis. And we create then sort of a solar-powered factory for producing renewable energy forms. And because of the high aerial yield of these organisms, this could be done at a scale big enough to generate terawatts of energy and really start to displace fossil fuels. And when we have a high lipid content material, we can extract the lipids to create what I'm calling here the biopetrol. And the rest of the biomass can go off to make other good energy things. I'd like to show this drawing. It shows the same information here, but in a much more attractive way. So here's the system. There's a loop here, and at the beginning of the loop, at the top, we have the sun, solar energy. We have some source of CO2. I show a power plant. It could even just be the atmosphere. And you're using the energy to fix the CO2 into the biomass. We then come along to the right side, and if we have a high lipid biomass, we can extract out the lipids, and we can make feedstock to replace things like petroleum to make transportation fuels. The rest of the biomass then comes around here, and it's some fermentation and various other things to make energy from the rest of the carbon. I show here a microbial fuel cell. Bruce Logan will talk a little bit about that in the next talk, but you can generate other forms of energy from it. Once you've gotten all the energy out, now the water and the nutrients are released, and they can just be recycled around. So the key thing here is that we have a loop, basically a loop system here, where the inputs are sunlight energy and CO2, and the outputs are various forms of useful energy, and the rest of it's going around and around the circle. And this is how we can avoid having water pollution and high water consumption, for example, on it. Now, just one last thing here. This is my last point I'm going to make here. That doesn't look good. I'm going to cancel this. Thank you. Okay. We do have a second strategy that we're working on right now, and I want to tell you about this. And that is have the photosynthetic bacteria pump out the feedstock on this. And particularly, we're working now on fatty acids that are feedstock to be producing things like jet fuel and diesel fuel. And we have an RPE project, this big RPE project on this. So the idea is we still use CO2 and sunlight as the prime resources, but now instead of producing biomass, we have let the biomass produce the product on it. And it looks something like this. You've got water, light, CO2 coming in. The organism here has been metabolically engineered to produce things like fatty acids. This would be used as feedstock for fuels or other materials down here for other beneficial uses. It's truly what we call a photosynthetic factory. The basic strategy is shown here. On the right-hand side, you see in black the normal patterns that the photosynthetic microorganisms do to fix CO2 and take it along a path, and eventually they're trying to make lipids. What we do is we add to this organism a thioesterase enzyme that diverts the material from this point off in a new direction to produce fatty acids that are then excreted from the cell, and we harvest them. And you can see down here, here's a flask where the lauric acid has been precipitated on the side of the beaker. It's good for visualization. That's not how we would harvest it, but it's good to look at the picture. And so with this strategy, we're basically not growing microorganisms. We're producing product on this. So since we're not producing biomass very much, we don't even need to use much nutrients as an input, and we don't have to harvest the organisms. It's a good deal. It becomes what I call a true photosynthetic factory. That is, those little organisms have energy from the sun, and they are working like a factory. They take raw materials in and they put raw materials out. And we don't harvest the factory, we harvest the product. So with that, I'm on my last slide. The take-home lessons for today. The take-home lessons today. Number one, society really needs a lot, very large amounts, terawatts of renewable carbon-neutral energy to replace fossil fuels over some next decades. Photosynthetic microorganisms can produce a lot of high-energy biomass or feedstock, and because of their high aerial yield and not competing with agriculture, they have the potential to do this at the scale that we actually need it done. They do it in a water slurry. They don't do it out there. And we can then have more or less a closed loop for the water and a closed loop for the nutrients, eliminating the pollution and water consumption problem. When we do this, we've created a wonderful situation where now the water is working for us. It's the slurry form for the microorganisms where they live, and we can recycle it. It's the electron donor to get those high energy electrons that we need to fuel. Water is working for us, not against us, and we're allowing us to generate large amounts of renewable energy. And with that, I've come to the end, and here's my official title, and here is the title I like even better. Thank you.